Computing from Past to Present. About this course. Welcome to the Computing from Past to Present course. In this course, you'll learn about milestone events in the history of computing. You will discover why key concepts like accessibility and security have become essential qualities of information technology. Learning objectives. After completing this course, you should be able to describe milestone changes in computing over time. Compare and contrast programs and modern applications. Recognize the changes that the cloud is making to modern computing. Define accessibility. Recognize computer security fundamentals. About this module. Module 1. From big frames to personal computers. Introduction. In this module, you will uncover the roots of computing. You will discover what the first computing machines were like and which of their underlying elements you are using today. Learning objectives. After completing this module, you should be able to describe milestone changes in computing over time. Identify the developments that allowed computers to become multifunctional. Compare and contrast the role of hardware, software, and firmware. Computing before computers. Computing through history has been more evolutionary than revolutionary. Radical changes actually happened from continual progress. If I have seen further than others, it is by standing on the shoulders of giants. Sir Isaac Newton, 1643 to 1727, was an English natural philosopher and mathematician. Newton is famous for introducing laws of motion and gravity. The computational model that modern computers use takes ancient computing ideas and applies power and speed to them. Today's computer scientists accomplish stunning work. Their work continues the incremental steps computer science has taken over the decades. A big step toward modern computing, logarithms. In the 17th century, John Napier, a Scottish mathematician, discovered logarithms. With logarithms, scientists were able to create repeatable shortcuts to solve problems involving large numbers using addition, which was simpler than using multiplication. This might not sound like automation, but the idea that it was possible to create repeatable shortcuts to solve complex math problems paved the way for modern computational devices. For example, sailors used logarithmic charts to calculate navigational routes. Logarithms also fostered the invention of the slide rule. Early computing machines. People have been using tools to make calculations for a long time. Here are a few examples of the types of tools that have been popular in the past. Counting. Wooden and stone mathematical machines were in use in ancient Babylonia as early as the 3rd century BCE. Navigating. Soon after Napier's discovery, the sextant, a device for calculating navigation, appeared in 1632. Scales. The slide rule was in use as early as 1633. Amounts. The first mechanical calculator was built in 1623. The early days of modern computing. If you want to send an encrypted text message to a friend, you simply open your favorite messaging application on your device, tap out your message, and press send. This process is secure and instant and even happens over a public network. Imagine how you would be sending messages in the time before computers. The science of computing leaped forward in the industrial age. As the 19th century began, faster machines were in use to automate computation at a large scale. Computation happened mechanically through the use of gears and levers. For example, the Enigma machine, which was famous for encoding messages in World War II, used a series of rotors attached to keys that used mechanical levers. The levers would turn the rotors to create a cipher. The cipher would be written down by a clerk and sent clandestinely to its recipient. Compare this communication with today's instant text messaging. Early computing machines were large. Alan Turing and Gordon Welchman, working at Bletchley Park north of London, had the task of breaking the Enigma ciphers. The first machine they developed, the bomb, was massive. It weighed around a ton and measured 7 feet wide, 6 feet 6 inches tall, and 2 feet deep. It was an electromechanical device that ran through millions of computations in attempts to break Enigma's ciphers. The bomb was able to decrypt a cipher in about 15 hours. Today's computers do the same operation in just a few minutes. Computing evolved with electronics. In the mid-20th century, mechanical computing migrated to electronics. Vacuum tubes, transistors, and integrated circuits brought an increase in speed and power. With these technologies, engineers were able to build computational machines that used electricity rather than moving parts to perform calculations. As circuits became smaller and faster, computational power increased. Once these milestones had been reached, the rate of invention accelerated. Today's computer chips use integrated circuit technology. Moore's Law. Gordon Moore, founder and former CEO of Intel, predicted in the 1960s that the number of transistors in an integrated circuit will double about every 2 years. The first integrated circuit had just one transistor. Today's computer chips have in the tens of billions of transistors in just one small chip. Mainframes and multifunction computers. The earliest modern computers were the size of entire rooms and mainly focused on solving a single set of problems. IBM's Harvard Mark I weighed 5 tons and was 50 feet long. You would program it with paper tape, cards, and a typewriter. Its purpose was to perform addition, subtraction, multiplication, division, and some algebraic calculations very quickly. The result of these calculations went to the user in the form of more paper tape or cards. These computers had design and functional limitations, partly in the type of computation they were able to do, but even more by the types of interfaces you needed to use to work with them. An interface is like the counter at a postal office where you give or receive your mail. It lets you give data to the computer and get data from the computer. The move from tape to screens and keyboards was evolutionary. Today just a few of the interfaces that you use are touch screens, microphones and speakers, keyboards, and touchpads. Mainframes and terminals. Because the output from calculations was available on a screen, a computer lab was set up with multiple terminals. At terminals, operators were able to enter data on a keyboard and see the result on a screen while sharing time on the same computer. This type of computer is a mainframe, which is a central computer that does all the thinking or processing and sends the result to the dumb terminal. Its name came from the large frame of its cabinet. As computers became more capable and interfaces supported more options, like color screens that display graphics, mainframes did more work beyond mathematical calculations. Operators were able to use these central computers to create geometrical shapes for computer-aided design, CAD, and create complex visuals for geographical and mapping operations, making it smaller and faster. Another evolutionary milestone, personal computers. In the 1980s, the technology advanced to another major milestone. Engineers were able to put all the computing power along with screens and keyboards in a compact package. You were able to use a personal computer at home, school, or the office. IBM's work in this space helped make personal computing mainstream. In 1981, IBM introduced the IBM Personal Computer, price tag $1,565. 2 decades earlier, an IBM computer often cost as much as $9 million and required an air-conditioned quarter-acre of space and a staff of 60 people to keep it fully loaded with instructions. The new IBM PC was able to not only process information faster than those earlier machines, but also it was able to hook up to a home television set, play games, process text, and store more words than a large cookbook. Source: IBM Archives. The birth of the IBM PC opens in a new tab. After these initial offerings, innovation and development took off. Following Moore's Law, chips became more powerful and more compact, and interface technology improved with each year. Soon computing machines were only limited by the imaginations of the people using them. While the fundamental model of computing hasn't changed, computers are still computational devices. The advances in technology have enabled all the incredible games, productivity, social, and business functions that you can use today. Hardware, software, and firmware. When you think about advances in computing, you might first focus on the hardware. After all, it's the hardware that provides the interface's visual, audio, and tactile experiences with computing devices. With the advent of personal computers, engineers had to pair hardware with software to make the computers useful. It is true that software cannot exercise its powers of lightness except through the weight of hardware. But it is the software that gives the orders. Source: Italo Calvino, 6 Memos for the Next Millennium, Lightness, 1988. Software programs are the instructions that tell the hardware what to do. If the computer is to respond to a click from a mouse or needs to show a graphic on the screen, it's the software that tells the hardware what to do and when to do it. Software can be installed and uninstalled, added and removed, from a computer device. Software can easily be updated when necessary. Firmware, the supervisor. Firmware is similar to software in that it's primarily computer code that controls hardware. Firmware differs from software in the way it runs on hardware. It typically is stored on a special chip within the device and generally controls the hardware's most basic functions. Firmware is like a supervisor who always is in the background ensuring things work the way they're supposed to. Imagine you have a light bulb that you control with your smartphone. The light bulb connects to your home network router and enables you to change the color, brightness, and set an on-off schedule. That light bulb has a small computer in it. When you plug it into your light socket, it turns on the computer and runs some computer code. The computer code that runs tells the network adapter to look for a wireless network is the bulb's firmware. Firmware can be updated when necessary, but that typically requires some special instructions. Like computer hardware, software has come a long way since the early days. Today's computers and hardware, software, and firmware stand on the shoulders of the giants, the large computers, of the last few decades. IT professionals better serve the users of the present and future by having a good grasp of the evolutionary computing past. Move milestones and improvements. Here are some key areas where improvements have led to major milestones in computing. Explore more. Up until the mid-20th century, the term computer was for a job role. Check out When Computers Were Human, opens in a new tab, to learn more about women who helped launch the U.S. space program by calculating launch windows, trajectories, fuel consumption, and other data before machines were able to do this work. About this module. Module 2. From software programs to applications. Introduction. In this module, you'll learn about the processes people have devised to instruct computing devices. You will discover the role that technology has played in moving computer programming from mainly manual to almost automatic. Learning objectives. After completing this module, you should be able to describe the function of early computer programs. Define computing code syntax. Describe milestones in software program delivery. Distinguish between programs, applications, and firmware. One job to do: early programs. Early computer programs mainly focused on mathematical problems. Many of these problems were complex, but the programs didn't do much beyond solving these math problems. These programs were deep but not very broad. MOCAs, the oldest program. An early program developed in 1958 was a United States Department of Defense contract management program for mechanization of contract administration services that was named MOCAs. MOCAs simply managed contracts and payments. This program was still in use as of 2017, running on an IBM 2098 mainframe. MOCAs was the type of program that was developed in the early days of computing. Before hardware was able to support the type of supercomputing you enjoy today, programs were relatively simple and did fairly modest jobs. Just because a job is modest doesn't mean it's not important or robust. According to the MIT Technology Review, opens in a new tab, MOCAs has processed trillions of dollars for the Department of Defense and has endured for almost 6 decades and many attempts to replace it. How early hardware received instructions. Computer systems operate on a binary model. Computer programs contain combinations of 0 and 1 that tell computer hardware what to do. Think of a binary digit like a light switch. When the switch is off, the digit is in a 0 state. When the switch is on, the digit is in a 1 state. If your switch controls a single light bulb, there are only 2 states the bulb can be in, on or off. Now suppose you have 2 switches that function as a dimmer for the bulb. With 2 switches, your bulb can be in one of 4 different states. 1. When both switches are on, the light bulb is on full power. 2. When both switches are off, the bulb is off. 3. When switch 1 is on and switch 2 is off, the bulb is on at 33% power. 4. When switch 1 is off and switch 2 is on, the bulb is on at 66% power. Computers operate on a similar model. Using a simple binary model, computers produce a tremendous amount of work. The model also enabled early computer programmers to give the computer instructions with something as simple as a punch card. A typical punch card has 80 columns and rows of numbers. Programmers would punch out one number in a row. Each number was part of an overall program. Using the binary system, a punched-out number meant a yes state or indicated that the programmer wanted the computer to use that number. If a number was not punched out, it indicated a no state or don't use that number. Usually the programmer had to use a new card for each line of the program. The computer would feed each card in row by row, adding the yes numbers into memory to assemble the program. When all the cards for the program were loaded, the program would run. Source: Real-Time Computing, The SAGE Project, 1952-1958, Chapter 2 in the History of Computer Communications. This might sound rudimentary relative to the contemporary way of doing things. But this approach set the stage for the evolution of software development. The fundamental model hasn't changed. Computer code gets translated into a binary language that instructs the device on what to do and when. Explore more. Check out the IBM 029 card punch, opens in a new tab, to get a deeper dive into the golden era of punch card programming. Modern software delivery. Today's software isn't delivered on punch cards. Modern software is written in a variety of computer languages. Languages like Java or PHP, named after personal homepage tools, are designed to be human-readable so engineers are able to more easily use them. It would be very difficult to program computers using just ones and zeros. These human-readable languages then get compiled or translated into the binary language computers use. Here's an example of the code of a very simple Java loop. When you first look at this, you might not think it's very readable at all. But this is simply a matter of syntax, the terms the language uses. Syntax isn't specific to computer languages. Syntax is defined in every language. When you learn to write computer code, you're actually learning a new language. Syntax. Syntax is the set of rules that the computer uses to interpret code. Follow the computer's use of syntax in the following example. What is the code saying to the computer? Follow the computer's use of syntax in this example Java loop. Step 1. In the loop, the code tells the computer to run that code block 10 times, and each time through the loop, print to the screen the number it's on. The first time through the loop, it would show, or print, a 1 on the screen. Public static void main, string args. 4. Int I equals 0, I10, I++. System.out.println, I. The part of the code for this change is I++. Step 3. It would continue to increment its output until it reaches 10. Public static void main, string args. 4. Int I equals 0, I10. Summary. The computer ran the loop according to the syntax it knows for the Java language. In the following animation, you see that each time through the loop, the value of I increases by 1. Instead of having to punch numbers on a card to instruct the computer, contemporary programs are made up of many lines of code, from a few hundred to hundreds of thousands in very large programs, like the loop that instructs the device to help you do work and have fun. If you saw a sample of an old language that uses unfamiliar symbols, you might think that it's not a language at all. But once you learn the syntax and grammar, you will be able to easily read it. Programs and applications. What's the difference? When you want to create a spreadsheet or join a team meeting, you might pull out your laptop and load your favorite word processor or conference call program. If you want to play a quick game, send a text, pay a bill, or connect with friends, you most likely will pull out your mobile device and open an app. The program on your laptop and the app on your phone are software code. Is there a difference between the software that runs on these various devices? If there is a difference, it has to do with how the software is delivered, how much it depends on data from the internet, and how it interacts with the hardware it's running on. In the 1990s, people started using the term application program. Over time they dropped program and just said application. Programs, applications, and apps are variations of the same concept. They essentially are the same thing. They run code that controls the interactions you have with your device. When smartphones were introduced, they were unable to do many things that were possible to do on a laptop. The word processor on your phone and the word processor on your laptop had different abilities, even if they came from the same company. And printing from a smartphone was another challenge. Many printers used drivers, a kind of software that told computers how to work with connected devices. However, driver applications were large programs and were not available for mobile devices. If you tried to connect a printer to your smartphone, it did not recognize or use the printer. Today many mobile devices and the applications that run on them are now sophisticated and efficient enough to support just about any interaction you would have on a laptop or desktop computer. Driver. A driver is a program that controls a device. Generally, a driver manages functions that you would not interface with directly. There is a special category of applications that many companies are investing in. Web applications are a hybrid between a program that you install through an application store and a web page. Browsers now have the ability to do amazing things that before only were possible with a powerful program you had to install. Because of this, software developers are able to build full applications that create complex diagrams and run complex spreadsheet operations with sophisticated charts. Very graphic-intensive games are even possible in web apps. A web application is different than the other program types you've explored because they're delivered entirely online and run in the browser, or a wrapper app that you install to your device. What do you think? With this latest development, it's an exciting time to work in computing. What kinds of web apps would you want to develop if you were an IT professional? Enter your response in the provided text box. When you are finished, select Done. Writing an answer is a good way to process your thoughts. These answers are for your use only. You have the option to download your response and save it. It will not be saved in the text box when you move on in the course. Evaluate your thinking. Does your answer account for the following? Good thoughts. IT support gives you opportunities in many areas. You can start with traditional help desk and troubleshooting roles and easily move into new areas that are evolving or around the next turn. Evaluate your thinking. Does your answer account for the following? Have you considered emerging cloud technologies? Artificial intelligence, AI, and robotics are among the most exciting areas to explore. About this module. Module 3. Cloud Computing. Introduction. In this module, you'll learn what made computing move to the cloud. You'll learn how the cloud came to be and why it is becoming an important part of today's computing environment. Learning objectives. After completing this module, you should be able to explain the origins of the cloud. Compare and contrast distributed and non-distributed hardware. Explain over-the-air, OTA, software updates. Describe benefits of OTA software updates. Explain what an application programming interface, API, is. Describe how the cloud supports scalability. What is the cloud and why does it matter? The first documented use of the term cloud computing was in an internal document at Compaq Computer, which later merged with the Hewlett-Packard Company. The name might have come from flowcharts that symbolized the Internet with a cloud icon. Regardless of the origins, the term cloud generally refers to the Internet. The term started as a technical term but is now common in everyday language. Source: MIT Business Review, opens in a new tab, October 31, 2011. The cloud, particularly in technical environments, is the set of services and storage that companies and users have come to depend on. For example, in a business plan, engineers might refer to a critical part of their infrastructure as being in cloud storage or using cloud services. In this context, they're referring to business services that are internet-based but most likely are being developed, deployed, and maintained by their company or a trusted partner. When businesses use the cloud this way, it is critical to their operations. And this is what makes it important. Suppose you are unable to stream a movie or listen to your playlist one evening because the internet went down. While this might be an inconvenience, it's unlikely that you'll suffer irreparable loss because of it. But when businesses rely on local systems for data storage and services, failure of those systems might have a significant impact on their operations. Using the cloud for data storage and services provides an important backup and recovery system to run their business without interruptions. For individuals, the cloud can provide an extra measure of protection from system failures or data corruption to support essential parts of their lives. For example, you might store critical legal documents on cloud storage. Breaking apart hardware functions. In the early days of the Internet, the cloud, individual, high-powered computers did all the work needed to support web pages and store files. These computers were the first servers. An individual server might have a number of websites running on it. The disk drive on that computer stored all the files needed for that site. In the early days, it was common for small businesses to have their company's websites running on a server under some person's desk. Imagine how fragile this was. As internet technology evolved, server farms developed where hundreds and then thousands of servers, networked together to share the tasks, or workloads, involved in delivering hundreds of websites and services. Further evolution enabled the separation of the actual hardware functions. Today cloud servers are built for specific hardware functions. Cloud server farms have thousands of computers designed specifically for large data storage and rapid transfer of that data to and from the disk drives. Other servers are built specifically to process data, or compute power. Still others handle networking or running specialized software. As the cloud continues to evolve, the computers that run various services will become more specialized, run faster, use less power, and become easier to maintain. These advances will help the cloud become more integrated into what you do every day. If it isn't already, the cloud truly will be a utility as important as electricity and plumbing. Updating software. The cloud has also made a significant impact on how software is updated. Before operating systems, the software used to run the basic functions of a computer, became more integrated with the cloud. You would update your software with plastic disks, which were called floppies. You had to go out and buy them at special computing stores or order them through the mail. To use a floppy, you had to physically insert it into your computer's cabinet. The update might take a very long time and prevent you from using your computer for another purpose until it was complete. If you worked for a large company, you might have to wait for a specialist from your computer department to install and configure the update on your system. Later on, it became possible to get some updates through a local area network, LAN, but installation would still require advanced skills. The cloud changed all that. With devices connected to the cloud continually, pushing updates or over-the-air, OTA, updates became possible. Operating system updates now happen in the background automatically. Many applications update without the user ever knowing it happened. When they load an application, the new features are available. Automatic updates are very important in critical security situations. If software, or a component of a large software application, has a security bug, the manufacturer is able to quickly push out an updated version with a fix for the vulnerability. OTA updates are for the benefit of the customer, not the manufacturer. Some IT professionals might push out incomplete or buggy software in a cloud update. We will just fix the bug sometime after release, the company might say. But this is an abuse of OTA. Software engineers work to release stable and bug-free software. Breaking software up into services. Adopting the same approach as hardware engineers who distributed functions to custom-built servers, software engineers have used the cloud to distribute software. Imagine you're on your favorite banking application on your mobile phone. You want to add another account to the application to keep track of spending. As you add the account, the application fetches account data from another provider, say a credit card company, and the data shows up in your banking application. The service that fetches the data might not be on the application installed on your phone. Instead, the application calls out to software on the cloud which has the conversation with the credit card company and returns the data securely to your phone. By distributing software functions in this way, software engineers are able to keep applications smaller, making download and load times smaller. Engineers can more easily update key functions. If software retrieves data from servers in the cloud, engineers are able to update that software and the apps on users' phones so they can use it immediately even if an application that uses it wasn't updated. When software on a device calls software in the cloud, engineers sometimes refer to this as making an API call. API stands for Application Programming Interface. When you want to call a family member, you pull up the phone application on your mobile phone, type or say the number, and touch the call button. The other person picks up and you now have a conversation. This is how an API works. An API is software that performs a specific function but doesn't have a user interface, something you interact with directly. Rather, it has an interface that other software uses. When an API is on the cloud, it has a web address. When software calls the API using that address, the call initiates a conversation with the API so the software can send and receive data. The following diagram shows how an API is called using a standard HTTPS request. The request is the URL of the API along with parameters that the API uses to fetch the correct data. More and more applications rely on cloud-based APIs today. As an IT support professional, prepare to be aware of which APIs software is supporting as you seek to troubleshoot issues. For example, suppose the software you're supporting depends on an API to retrieve data and a user calls complaining that they are not able to get their data. You might ask a simple troubleshooting question like, "Are you connected to the internet?" You'd ask this question only if you knew that the application uses an API. Scalability in the cloud. The cloud offers a great capability, scalability. Imagine you want to plant a garden. You rent a small tractor to haul in some soil. As you get into the work, you find large rocks in the yard and you need to remove them. However, the tractor you rented isn't large enough to remove the rocks. So you go out and rent a bigger tractor. Once you remove the rocks, you find your larger tractor is too big to fit into a part of the space where you need to remove some dead plants. So, you then rent a wheelbarrow to haul the dead plants out. The problem you deal with in this situation is scale. It would be better if you were able to rent one piece of equipment that was able to adapt to whatever need you had. In the days before the cloud, if you needed more power on the computer you had, you either had to upgrade, buy another computer, or borrow one. This was really inconvenient if you only needed the extra power temporarily. And many people spent a lot of extra money on power they never used or needed. The cloud has helped address this scale problem. Many services are available in the cloud now where businesses and individuals pay for only the capacity and power they use. If a user needs more storage, they pay for it when they need it and scale back, paying less when they no longer need it. If a media company is having a big event like a major sporting competition and expects streaming demand to be high on a given day, they are able to use cloud services that automatically will scale up when demand is high and scale down when it gets back to normal. This makes for a better user experience since the company doesn't experience broadcast outages and the streaming capacity automatically adjusts to demand without the company having to manage it. Scalability at work. See scalability at work in the following actions. Scaling up. Scaling down. About this module. Module 4. Making computers accessible. Introduction. In this module, you'll learn that accessibility enables everyone to use computers and ways in which hardware and software enables access for all. Learning objectives. After completing this module, you should be able to compare and contrast usability and accessibility. Describe hardware support for accessibility. Describe software support for accessibility. Using computers in the early days. When a new technology is emerging, many engineers are striving to get the technology to just work. The focus is on basic functionality and little attention is paid to how people will actually use the technology. How you interact with a technology is called usability. The easier a technology is to interact with, the more usable it is. The reverse also is true. Early computers tended to be difficult to use. For instance, punch cards were cumbersome and very prone to error. Imagine dropping a pile of thousands of punch cards and trying to get them back in order. The first screens available for computers were monochrome and didn't support graphics. Monochrome screens would either be black and white or black and green. To get these computers to work, you had to know obscure commands and type them in the right order. Keyboards and mice became widely available in the early 1970s. Touch screens didn't appear until the 1990s. These improvements, while significant, focused on the majority of users. People that fell outside the majority, like the visually and hearing impaired, had to find their own solutions if they wanted to use these early machines. Today, addressing the needs of the minority is a fundamental aspect of software and hardware design. What is accessibility? The broad use of technology is called accessibility. The idea is that technology is accessible by anyone that wants to use it. Usability and accessibility go together. If people with impairments have access to technology, then they also ought to find that technology usable. At this stage in the evolution of computer technology, accessibility is as important a consideration as security and usability. For computer technology to be accessible, any function on the device or software is available to anyone who wants to use it. While the context for accessibility sometimes focuses on people with impairments, it's more inclusive to think about accessibility as providing access for all. Technology must support equal access. Making software and hardware accessible is multifaceted and can be quite complex. Because of this, thinking about accessibility at the beginning of an engineering project will usually be far more beneficial than trying to retrofit an inaccessible design after it's been built. There are many ways that engineers can make their technology accessible. It's not always essential that the engineer provide all the software and tools those with impairments would need to use the technology. It is important, however, that engineers understand how an impaired person uses the technology and provide the means by which they access it. For example, many visually impaired people use screen reader software. This software extracts text on a screen and speaks the text to the user. The engineering team wouldn't need to include the screen reader software with their software. They would, however, have to make sure their software is compatible with popular and compliant screen readers available on the market. The following table highlights the differences between usability and accessibility. Both concepts are important in user interface design and, working together, create an inclusive experience. Usability. Focus on user experience, UX, design. Accessibility. Focus on people with disabilities. Usability. Quality. Accessibility. Technical design. Usability. Satisfaction. Accessibility. Interface features. Usability. Efficiency. Accessibility. Addressing discrimination. Usability. Effectiveness. Accessibility. Providing everyone with the same experience. Usability. User-friendly. Accessibility. User-friendly. How hardware supports accessibility. Specialized hardware devices that people with impairments use to access computer hardware is called adaptive technology. Here are a few adaptive technologies. Locator dots on the keyboard for commonly used keys for those with visual impairment. Braille embossers. Speech output systems. Speech recognition products, to dictate assignments and navigate the internet using voice commands. Mouth sticks, head sticks, or other pointing devices. Modified keyboards, expanded, mini, or one-handed. Trackballs or other input devices, as alternatives to the mouse. Keyboard emulation with specialized switches, for scanning or Morse code input. Speech input. Source, assistive technology, opens in a new tab, Access Computing, University of Washington. These specialized hardware devices are essential for some types of impairments. Hardware developed for non-impaired users accommodates a wider range of users. For example, a larger and visible on/off switch not only helps those with motor or visual impairments but also makes a system easier to use for everyone. When you get a text message or a phone call and your phone vibrates, it's using haptics to inform you of the message or call. Some phones will slightly buzz when you type on a software keyboard. Others will gently vibrate when an alarm goes off. Haptics is physical feedback that some event occurred on your device. These software and hardware combinations work together to make the device more usable and accessible. One of the first use of haptics was in 1969 to provide assistive technology for people with low or no vision. Source, vision substitution by tactile image projection, opens in a new tab, NASA's/ads, harvard.edu. How software supports accessibility. Much of the innovation in accessible technology is happening in software development. Creating devices that are accessible to people with impairments has become a primary design principle for many companies. If you open the accessibility settings on your phone, you can find a number of ways that the phone's operating system software accommodates a variety of impairments. Here are 5 important examples. High contrast. This setting assists people with low vision see the difference between light and dark areas of a screen. The higher the contrast, the more distinction there is between these objects, increasing their visibility. Audio. Audio options are showing up across operating systems to help people with low or no vision navigate the user interface. Some devices include an option that will read items on a screen as a user navigates through the user interface. This technology is similar to screen readers but is integrated into the operating system. Voice control. The ability to control a user interface or application with voice is becoming more mainstream. This is being made possible partly because artificial intelligence, AI, and natural language processing, NLP, systems more accurately understand human speech. Many mobile phones support dictation. You may try dictation by creating or replying to a text message on your phone and pressing the microphone key on the keyboard. As you speak, the application will add your words into the message input box. This feature is a good example of one that may have been designed for those with motor skill impairments but benefit every user. Motion control. For people with motion sensitivities, many devices enable users to reduce the amount of motion used in interface elements. For example, some operating systems animate the opening and closing of an application. Motion control turns off or reduce that animation. Motion control also may prevent videos from playing automatically. Keyboard options. For people with motor skill impairments, being able to press a key once and have it repeat or having more time for a key to register a press can have a significant impact on that user's ability to interact with a keyboard. Many of these features depend on good software design for applications and services. For example, all user interface elements like buttons, text boxes, and images must include alternative text, alt text. Screen readers read alt text to identify otherwise inaccessible visual elements like photos, diagrams, and videos. You add alt text during development time. Check your knowledge about how accessible technologies help people. Explore more. Check out the Web Content Accessibility Guidelines, WCAG, opens in a new tab. These guidelines provide comprehensive accessibility standards and tutorials. About this module. Module 5. Identity and Security on Computer Systems. Introduction. In this module, you'll learn about the systems that IT professionals have developed to keep computer users secure. You will discover why it is important to use security measures like passwords and biometrics. Learning objectives. After completing this module, you should be able to summarize key aspects of computer security. Compare and contrast passwords and biometrics. Describe ways IT professionals are able to keep users safe. Explain where computer security is heading in the future. Early methods for keeping a computer secure. Think about all the things you do on your mobile phone, tablet, laptop, or other computing devices each day. Your list might include messaging, online shopping, posting to social media, filling out forms for a bank or the government, or perhaps sending photos to friends and family. While you use a lot of content on your devices, you also send a lot of data to different places on the internet. Some of that data, if it got into the wrong hands, might cause you harm. As computer science was developing, securing a computer might involve little more than locking a door. Before computers were networked, the risk of a breach of sensitive data was more about securing the physical machine than having to prevent a computer from being hacked remotely. Usernames and passwords. Risks to computer systems and more importantly to the data they stored and processed dramatically increased with the onset of networked devices. Keeping machines secure largely relied on usernames and passwords. Ideally only the person who created them knew what they were, and they created a unique digital identity. This identity was mainly a front door identity that allowed or prevented people from accessing the computer. Usernames and passwords are like the security guard in the lobby of an office building. Assuming no other security measures are in place like locked doors or security cameras, once someone gets past the security guard, they have freedom to access the entire building. Beyond the front door, protecting user data. Usernames and passwords are still common today. Many users create weak passwords, however, because they're easier to remember. Or users reuse the same password many times. If that password is broken or hacked, other digital resources that use the same password are at risk. Protecting a computer with strong passwords that use a mix of uppercase letters, lowercase letters, numbers, and special characters will be very effective at preventing security breaches. Password protection layers. When you use a device in today's computing environment, you might need to provide a password, scan your face, use a fingerprint, or enter a code not only to access the device but to access individual resources on the device. And you might need to confirm your identity several times. This next layer of security represents a big development in securing user data. Even if someone was able to hack into a device, they would be prevented from getting access to key data of the user's device. Users now also protect individual folders and files with unique passwords. What are biometrics? Biometrics are the security methods that use your physical characteristics. Devices that recognize your face, fingerprint, or retina are using biometrics. Devices are enabling biometrics to remove the need to remember dozens of unique passwords. Since biometric security is much more difficult to break, securing your data with your face or fingerprint is not only safer but it's also much more convenient to use. Enabling security on various parts of the computer system and for folders and files would be similar to putting locks on all the doors of the building and putting locks on file cabinets and other resources. Even if someone got into the building, they would have to break other security measures to access your sensitive data. Where security is heading. When you take a photo on your phone, you can save the photo to the cloud. This will be convenient because it provides an automatic backup of your photos, can save space on your phone, and makes it easier to access your pictures from anywhere. It also introduces a new possibility of having your private information compromised. Attack vector. Attack vectors are ways in which an attacker can compromise a system. IT professionals work to define and then minimize attack vectors. Protecting users and data. Many cloud services, like online storage, are developing systems to protect data in a number of ways. 1. Some services encrypt data as it moves over the Internet. This is called encryption in transit. 2. Some services encrypt data on the storage system itself. This is called encryption at rest. Only the tools designed to access the data can decrypt the files. Even messaging software is now encrypting messages in transit to keep unwelcome people from seeing the content of those messages. Many devices and websites are using sophisticated methods to find patterns in user behavior and alert you if things happen on a device or website that fall out of those patterns. Credit card companies have done this for many years. The assumption these companies make is that you will generally use your card in your home area. If, all of a sudden, the card is used in another country or used on the same day in 2 locations, the credit card company takes a better safe than sorry approach and alerts you that someone might be using your card fraudulently. Heuristic. Detecting patterns and then using those patterns to predict future behavior is sometimes called a heuristic. It comes from a Greek word meaning discovery. Engineers define what behaviors would be useful to observe and then figure out how to apply those observations to create security alerts. Computer systems watch for the same type of behaviors. Suppose you generally log into a website from a specific geographical location like from your home or the area around your home. The website might keep track of this behavior. If the website detects someone trying to log in from another part of your country, it will then alert you and ask if it's actually you. This type of alert can save the user and the website operators from serious problems. Hardware manufacturers also are developing more sophisticated biometrics to keep computer systems safe. Biometrics also are being integrated with software so users can log into websites or applications using the same biometrics they use to gain access to their device. Security challenges for IT professionals. IT professionals must keep computer systems secure and help users manage security. Professionals working on network security continually have to keep devices and systems up to date, stay informed of emerging threats and respond quickly to them. They also need to manage network access to systems, which they do with a special software called a firewall. Security breaches occur most frequently on networked computers due to errors, oversights, or inaction by users. IT professionals are responsible for ensuring their users are adhering to security measures. Here are some things IT professionals can do to ensure their networks are safe. Education. Informing users of potential security threats, teaching them how to create strong passwords, and showing them how to recognize emails from hackers must be a regular practice of IT professionals. While an IT professional is to be actively involved in the daily security of a system, educating users creates a team of security ambassadors who are able to help keep themselves and others safe. Tools. Tools that help users secure their software and hardware can empower these users and create good habits. Software like a password manager or hardware like a laptop cable lock coupled with education on how to use them goes a long way toward keeping users safe. Prevention. The old saying, an ounce of prevention is worth a pound of cure. Education and tools both function as preventative measures. But IT professionals need to ensure virus scanners are up to date, operating systems are current, and updates are vetted before being installed. These types of activities help prevent problems before they happen. Recovery and troubleshooting. Sometimes users forget their password and need help accessing their software. A user who has clicked on a phishing email might worry that their data was accessed. Sometimes breaches occur and a virus infects one or more computers. In these situations, IT professionals need to have action plans for every scenario they anticipate and put those plans into place to get users back to productivity. Now that you've learned about how IT professionals face challenges, try to identify a few examples of these security measures. You've come so far and learned so much. You learned where computing came from and the technological developments that keep it going. Now that you've completed this course, you should be able to describe milestone changes in computing over time. Compare and contrast programs and modern applications. Recognize the changes that the cloud is making to modern computing. Define accessibility. Recognize computer security fundamentals. Key points to remember. 1. Computing through history has been more evolutionary than revolutionary. 2. Logarithms enable scientists to create repeatable shortcuts to solve complex math problems. 3. The science of computing leaped forward in the industrial age, and in the mid-20th century mechanical computing migrated to electronics. 4. Integrated circuit technology transformed computers in size, speed, and power. 5. In the 1980s, a major milestone was the introduction of the personal computer, when engineers were able to put all the computing power along with screens and keyboards in a compact package. 6. Computers use a simple binary model to process their work. 7. Modern software is written in a variety of computer languages. 8. Syntax is the set of rules that the computer uses to interpret code. 9. The difference between a program and an application has to do with how the software is delivered, how much it depends on data from the internet, and how it interacts with the hardware it's running on. An app is software that runs on a mobile device. 10. The cloud is a set of services and storage. 11. Cloud servers are designed specifically for large data storage, rapid data transfer, data processing, data, compute power, network management, or running specialized software. 12. The cloud made a significant impact on how software is updated and enabled over-the-air, OTA, updates. 13. The cloud enables scalability. 14. How you interact with a technology is called usability. The easier a technology is to interact with, the more usable it is. 15. The broad use of technology is called accessibility. The idea is that technology is accessible by anyone that wants to use it. 16. Engineers must understand how an impaired person uses the technology and provide the means by which they access it. 17. Specialized hardware devices that people with impairments use to access computer hardware are called adaptive technology. 18. Haptics is physical feedback that some event occurred on your device provided by software and hardware combinations that work together to make the device more usable and accessible. 19. Risks to computer systems dramatically increased with the onset of networked devices. 20. Usernames and password keep devices secure because they create a unique digital identity. 21. Protecting a computer with strong passwords that use a mix of uppercase letters, lowercase letters, numbers, and special characters will be very effective at preventing security breaches. 22. Biometrics are the security methods that use your physical characteristics. 23. Some services encrypt data as it moves over the Internet, encryption in transit, and some services encrypt data on the storage system itself, encryption at rest. 24. Many devices and websites use sophisticated methods to find patterns in user behavior and alert you if things happen on a device or a website that fall out of those patterns. 25. Engineers use heuristics to define what behaviors would be useful to observe and then figure out how to apply those observations to create security alerts. 26. Professionals working on network security continually have to keep devices and systems up to date, stay informed of emerging threats, and respond quickly to them. 27. IT professionals are responsible for ensuring their users are adhering to security measures.